Good evening, classmates. Good evening, sir. Today I will be presenting my first review article, and the title of the article is Potentials, Limitations, Co-Benefits, and Trade-offs of Biochar Applications to Soils for Climate Change Mitigation. The authors are shown on the slide, and they are from Norway. This article was only recently published in 2019 in the journal Land by the publisher MDPI. Moving on to the main driver of this study, I'm sure we are all familiar with the Paris Agreement. We all know that technological development and economic growth have led to rising CO2 emissions from the combustion of fuels. And this slide shows the global temperature increase by the year 2100. The line here shows the baseline delta temperature based on the pre-industrial average. So the baseline is 0. This is the pre-industrial average. And we are currently here at 1 degree higher, 1 degree Celsius higher than the pre-industrial average. If we continue doing our business as usual, the emissions will cause the rise of temperature by 3.3 degrees Celsius. But if the countries who pledged in the Paris Agreement fulfill their promise, then it will only be 3 degrees Celsius increase from the pre-industrial average, which is not far from the 3.3 degrees increase if we do business as usual. And comparing that to the limit set by the Paris Agreement, which are 2 degrees Celsius from the pre-industrial average, and the more ambitious goal is 1.5 degrees. Um, it's almost double of the limit set in the Paris Agreement. This slide shows another figure which shows the temperature projections based on historical data, but the y-axis here shows the global greenhouse gas emissions in gigaton carbon dioxide equivalent, and the x-axis shows the timeline. And as we can see from the historical data, the greenhouse gas emissions has an increasing trend. And if we do nothing about it, the trend will just continue to increase. But if the countries fulfill their pledges, it will slightly dampen. However, this is still far from the Paris goal, which is 2 degrees and 1.5 degrees Celsius increase from the pre-industrial average. By the way, the Philippines is actually one of the countries who pledged uh, in the Paris Agreement, and our pledge is 70% below our business as usual emissions by the year 2030. And as scientists, it's our role to come up with solutions. That's the heavy burden placed on us. And we need to think fast because it's almost 2030. It's less than 10 years from now. Thus, the birth of negative emission technologies, or otherwise known as greenhouse gas removal technologies. This slide shows the examples of negative emission technologies, or we can also uh, use the acronym NETs. And the examples are afforestation and reforestation, which is conversion of non-forested land to forested land through planting and seeding. We also have bioenergy with carbon capture and storage. I'm sure we are all familiar with bioenergy, but after extracting the bioenergy from biomass, we capture and store the carbon, therefore removing it from the atmosphere. Next, we have enhanced weathering. It's using natural or artificially created minerals which absorb carbon dioxide and transform it in other substances. We also have ocean liming, use of calcium hydroxide or calcium bicarbonate. Um, we we pour it on the ocean surface water and thereby accelerating the uptake of carbon dioxide from the atmosphere. We also have ocean fertilization, wherein we put iron, phosphate, nitrogen on the ocean that would sink the dead biological matter into the bottom of the ocean. And we also have direct air capture. It's the absorption of CO2 directly from the atmosphere, either by wet scrubbing or amines. And lastly, which is the topic of this paper, we have biochar application to the soil. So biochar, which is also considered bioenergy, is produced, but instead of extracting the energy from the biochar, we bury it in soil so that we prevent the biotic carbon from going back to the atmosphere through decomposition. What is the role of this review paper? It provides an assessment of the state-of-the-art of biochar systems for soil amendment, taking a life cycle perspective. And life cycle is actually an analysis from the cradle to the grave of any product. And our product being considered here is the biochar, and the application is as amendment to the soil. It also studies the relevant environmental aspects or environmental impacts. And it discusses the variety of effects that biochar can have on the climate system, which is a very relevant topic right now because of the Paris Agreement, which is uh, driven by the climate change. And I put this image here to show the environmental footprint. By the way, this paper has over 271 references. To give an overview of biochar, it's made from pyrolysis. And if you're not familiar with pyrolysis, it's the thermal decomposition of biomass at high temperature in the absence of oxygen. Biochar has the following benefits. It acts as carbon sink because it sequesters carbon dioxide as it grows, when the plant grows. And then after being transformed into biochar, it improves soil quality, thus increasing fertility, and it increases the water holding capacity. However, despite these benefits, it has potential impacts on climate change and eutrophication, acidification, and human health. What are the sources of biochar? We have uh, woody biomass, herbaceous and agricultural biomass, and we have aqueous biomass, manure, sewage sludge. And here are some examples of the biomass and as they are converted to their corresponding biochar. Now, carbon-rich feedstocks such as woody and herbaceous materials produce more stable biochar because of the lignocellulosic structure. On the other hand, organic waste products such as manure, sewage sludge, or food waste contain less carbon, but they are richer in nitrogen, phosphorus, and potassium, or NPK. And we know that NPK are components of fertilizer. However, biochar made from organic waste product has disadvantages because it's more alkaline and have higher salt content, which has negative effect on plant growth. And there is a higher risk that biochar can contain toxic compounds such as dioxins and furans, which has potential toxic effects on soil. So those are biochars that are made from manure and sewage sludge. And finally, another disadvantage of biochar made from organic waste is it contains higher heavy metal concentration. The slide shows a summary of biochar production operating conditions. And we have three pathways. We have slow pyrolysis, fast pyrolysis, and gasification. There are actually three products in pyrolysis. We have the biochar, which is a solid product, the bio-oil, which is a liquid, and the syngas, which is a gas. Among these three pathways, the best one for biochar production is low pyrolysis because of the higher yield. This may be a typo error. It should be a higher range. And the fast pyrolysis and gasification are more suited for energy recovery purposes because they favor production of bio-oil and syngas. What are the impacts of biochar on soil carbon cycle? We have both negative and positive impacts. As for negative, biochar can release dissolved organic carbon and be leached out and transported to fresh water systems. Because it contains the carbon, then most probably we cannot stop it from leaching out. And another negative is biochar particles can also be transported by the wind after soil incorporation. Because biochar particles are very small, then the wind can carry it. As for positive effects, obviously it sequesters atmospheric carbon dioxide during its growth, during vegetation growth, and it stores a large fraction of this carbon in soils in recalcitrant form. Recalcitrant means difficult to destroy, or it's very stable. It can stimulate microbial activity after application, and it can increase soil microbial biomass. How about biochar's impact on nitrogen and phosphorus cycles or NNP cycles? We only have positive impacts. Biochar beneficially increases nitrogen fixation in soil by 63% and decreases nitrogen leaching by 26%. Increases N fertilizer efficiency. In fact, the use of fertilizer can be decreased due to the application of biochar, or in other words, biochar can serve as fertilizer. It reduces nitrous oxide and NOx soil emissions, and it increases the plant available phosphorus in soils by 45%, and the microbial biomass phosphorus by 48%. The same way, it can replace the P in the NPK fertilizers. How about biochar's impact on the water cycle? Biochar increases the water holding capacity of soil, and it improves the plant water use efficiency. Next, you have biochar's impact on climate. This slide shows two scenarios. We have on the left under cultivated field, and on the right under fallow conditions. So what does fallow means? It means it's a cropland, but there's no uh, produce, or there's no plants yet, and it's being ready, either being readied, or the cropland is allowed to rest. A positive value means the effect is increased. A negative value means the effect is decreased. An equal sign, it means uh, unchanged, and a question mark means there is limited data. First, we discuss the soil organic carbon. Obviously, it's positive for both cases because biochar contains a lot of carbon and it increases the soil organic carbon. Next, we have the soil inorganic carbon, which are the calcium carbonate or carbonic acid. For both cases, it might increase the soil inorganic carbon, but more evidence is needed. That's why there's a question mark. For the albedo, or the reflection of light, biochar tends to make soils darker, hence reduces the surface albedo. Here in the left part of the screen is a figure that shows that a light surface actually has a higher albedo compared to a darker surface. As for the soil emissions, it depends on which type of gas. There are various gases that are involved in soil emissions. We have nitrous oxide, methane, NOx, and ammonia. So it depends on which type of gas. Some are increased, some are decreased. For the water retention, as mentioned, biochar increases soil water retention and plant available water. For the evapotranspiration, um, it has contrasting effects between the cultivated field and the fallow. And it depends on the soil condition and climate. For the black carbon, or these are the particulate matter, during application of biochar, tilling operation, microparticles of black carbon can be transported by the wind. As for the soil temperature, it increases the soil temperature for the fallow. Biochar's effect on food security and soil quality. We both have negative and positive effects. For the negative, it immobilizes pesticides and reduces the efficiency of treatments. Biochar is like activated carbon, so it acts like an adsorbent. And the effect on pesticides is that most probably pesticides get absorbed into the biochar. That's why it has this impact. And in the same way, herbicides are also made less efficient, most probably because it also absorbs the herbicides. And volatile organic carbon or VOCs on biochar and free radical generation may impair seed germination. As for the positive effects, biochar increases the agricultural yield by 25%. It increases the soil moisture, which in turn increases the yield. The albedo effect may warm soils and ease germination, just like what we see in greenhouses where we allow seeds to germinate. And greenhouses are actually warmer than the ambient temperature. It can help prevent soil erosion. Continuing biochar's impact on food security and soil quality, let's go back to the negative effects. The ash content may increase salination risks and stress because ash is made up of the oxides of metals. It can bring polyaromatic hydrocarbons or PAHs, dioxins, VOCs, and heavy metals to the soil depending on its feedstock and production conditions. As mentioned, organic wastes have more dioxins and furans and heavy metals. So depending on the feedstock, it can have this negative effect. Moving back to the positive effects, it improves plant response and alleviates stress on crops under drought and salt stress. It can act as a liming agent and can increase soil buffering, or it can control acidity. It can immobilize heavy metals through sorption, precipitation, and pH oxidoreduction reaction. As mentioned, biochar is like an activated carbon which can absorb heavy metals and thus this positive effect. Moving on to biochar's impact on toxicity and ecosystems. We have negative effects, gas emissions during pyrolysis and dust and black carbon emissions from soils. I experienced this firsthand during my thesis. There is really a huge amount of dust and particulate matter being formed in the production of char. Black carbon particulate matter of these sizes, 2.5 micrometer and 10 micrometer, which are toxic to humans and ecosystems. So these are formed in the production of biochar, and when we apply biochar in the soils, although we bury it, there is a risk that humans are exposed to this particulate matter. Some of the positive effects on toxicity and ecosystems: biochar reduces nitrate leaching, but it has a mixed effect on ammonium and phosphorus. And we know that nitrogen and phosphorus leaching from agricultural fields cause eutrophication in water bodies. Biochar decreases bioaccumulation of heavy metals in plants, thus reducing risk toward human health, most probably because it absorbs the heavy metals instead of the plants absorbing the heavy metals. Continuing with biochar's impact on toxicity and ecosystems, another negative impact would be leaching out of dissolved organic carbon, which are toxic to terrestrials and water ecosystems due to heavy metals and polyaromatic hydrocarbons. On the other hand, another positive effect is that it reduces the fate of pesticides in groundwater and toxicity. Because it absorbs the pesticides, then it holds the pesticides in place so that it will not reach anymore the groundwater. Moving on to the life cycle assessment of biochar systems. The y-axis shows the climate change GWP, or the y-axis shows the global warming potential, or GWP, in tons carbon dioxide equivalent per ton of feedstock, and then the x-axis shows the different phases in the life cycle. A positive value, so this is the positive area. A positive value means that CO2 is released to the atmosphere, while a negative value means CO2 is sequestered from the atmosphere. As we can see, um, the supply chain and pyrolysis of biochar causes the release of CO2 to the atmosphere. However, it has avoided emissions, most probably because it uh, decreases soil emissions. And because we prevent the carbon from going back to the atmosphere by burying it in the soil, the effect of carbon sequestration here is a negative value for the global warming potential. And other effects on the soil also corresponds to a negative value in the global warming potential. For a total effect of this range. So by the way, the dots here are data from different studies. The diamonds represent the outliers, and the color of the dots represent the different types of feedstock used. Summarizing biochar's performance from the previous slide, from the different LCAs performed, the performance varies between a net emission of 0.04 tons of carbon dioxide per ton feedstock to a net reduction of 1.67 tons carbon dioxide per ton of feedstock. So what does these values mean? This actually shows the range of biochar's performance. This lower value here corresponds to this point here, and this upper value 1.67 is actually here, negative 1.67. So 0.04 and negative 1.67. But 0.04, since it's positive, it means net emission. And then the negative 1.67, since it's negative, it means net reduction. The wide range of values is due to the different assumptions in the LCA studies, such as type of feedstock, biochar stability, and soil emissions. I really hope that whatever happens in the future, we will not end up in this worst case scenario. Even ending up somewhere in between is better. The next figure shows biochar's potential as compared to the targets set by the Paris Agreement. And it shows that biochar can indeed contribute to the necessary CO2 sequestration goals set by the Paris Agreement. So you can see here, these are the different timelines or deployment horizon, and in each year, biochar can actually reach the goal set. In each year, it can actually have a contribution on the goal set. It may not meet the entire goal, but at least a percentage of the goal set. So this slide shows the summary of the previous slide. Using only forest or crop residues as feedstock, it can actually deliver 10% of the required carbon dioxide removal for the 1.5 degree scenario and 25% of the required carbon dioxide removal for the 2 degrees scenario. But if we use dedicated crops as biochar feedstocks, which means we intentionally plant crops for biochar, it can deliver 15 to 35% of the required carbon dioxide removal for the 1.5 degree scenario and up to 35 to 50% of the required carbon dioxide removal for the 2 degrees scenario. As we saw in the previous slides, there is a large variability of biochar impacts on the environment and climate systems. And this is due to the main aspects that control the environmental performance of biochar. Number 1, biomass feedstock type and biochar production conditions. Number 2, soil properties and local climate conditions. And number 3, biochar management and application practices. Therefore, there's no black and white answer or a definitive yes or no whether biochar has a negative or positive impact on the environment because we are just given a range of values from different studies and therefore a lot of gray areas in the application of biochar to soil. How about the land requirements and application rate? To reach biochar's full potential as a nets or negative emission technology, it requires 2 gigahectares, and that is 16% of the total global land area, and up to the total agricultural land area of 4.5 gigahectares. That's about 45 million square kilometer. As for the biochar application rate, it's commonly between 20 to 50 tons of biochar per hectare and could be as high as 150 tons of biochar per hectare. What are the social and ethical impacts of biochar? Technically, among the nets, biochar is one with the lowest ethical side effects. And this is because biochar is like a fertilizer that is being applied into the soil. Unlike, for example, in ocean liming or ocean fertilization, these solutions are not quite studied yet in large scale or pilot scale. It also provides an important social benefits to the most vulnerable farmers. On the other hand, it can also have adverse side effects on food security or natural ecosystems. So you can imagine the land use demand for biochar is really large. It competes with food in terms of land use. And it also competes with biodiversity in terms of land use. Biochar's long-term aging and effects on soils are not fully understood yet. There are no long-term studies yet. As for the summary and recommendations, biochar has many complex mechanisms. As mentioned, it has the albedo effect, black carbon emissions from soils, etc., leaching, or with water bodies through leaching of nutrients. But according to the author, biochar in soils presents relatively low risks relative to the other nets, and it can even improve soil quality. Thank you very much for listening. I'm now ready to take in your questions.